Hello everyone, my name is Hui, and I'm actually the PhD student in Armand University, and today the title of my talk is Spatial Object Recommendation with Hints, when Spatial Granularity Matters. And this work is cooperated with Baidu Research. And here's outline of our talk. So we are going to the first part. And as you know, there are a lot of related work on spatial object recommendation. Actually, this is a kind of important location-based service. In this kind of service, the most relevant venues or regions are recommended based on some important information like spatial, temporal, and textual information. And we argue that the user's preferences may vary at different levels of geospatial granularity. So for example, in this personalized interaction map application, and in Figure A and Figure B, users are located in different views of the map application. So in your left finger, you can find the global view of Los Angeles. There, it includes a lot of suburbs. Well, in the right-hand finger, you can find when user zoom in, it will show a lot of POIs. And in this work, we aim to answer the question, how can we satisfy users' requirements over different spatial granularities? And we model this problem as multi-level POI recommendation. You can find in this figure, suppose for this user, it may check in a big area, like a shopping mall. And he may also have a check-in at a particular POI, like historical museum. So in this work, for ease of illustration, we will consider either an area like a shopping mall or particular POI like history museum as POI. And these POIs will be organized in a POI tree. And you can find in this POI tree from top to bottom, we construct this tree based on the spatial containment relationship. Like in the CBD, it will contain some malls and the library. And in our problem, the input is we have one particular user and his historical interaction pattern, and the user-defined parameter key. And we want to return the top key most relevant POIs at varying venues, at varying levels of granularity in this POI tree. And there are a lot of related work on spatial object recommendation. So here we only list some important ones. So first type is category-aware POI recommendation. And in this kind of related work, they will assume the categories of POIs will matter when doing the recommendation because they are very important indicators to model users' preferences over their activities. So in their POI category tree, suppose the top level has food or entertainment. In the bottom, it may contain Asian restaurant or bar. And the second type of related work is recommendation with a spatial hierarchy. So in their work, they only try to use the spatial hierarchy information to alleviate the data sparsity problem, such that the overall recommendation performance can be improved. And therefore, in our work, we first want to define the multi-level POI recommendation problem. And we also try to use the POI tree based on the spatial containment relationship to provide POI recommendations at varying levels of spatial granularity. And well, the straightforward method to handle this problem is we can use a well-known POI recommendation algorithm such that in each level of POI tree, we can build a separate recommendation model. Well, this approach will have one drawback. because it can hardly use the mutual information between POIs at different spatial granularity levels. For example, when user prefer to visit a shopping mall because of he likes the coffee shop inside this mall. And so this is our core challenge in this work. How can we achieve a one-size-fits-all model to make recommendations at different levels? And in our approach, we have proposed an MPR model, and you can find in this framework figure. The upper part, we have listed the input and our framework and corresponding output. In our input is very easy to understand. You can find users may have different check-in information at different levels of POI trees. And also in advance, we need to construct this kind of POI tree based on the spatial containment relationship. And finally, we can do the corresponding recommendation and find the top key POIs in each POI level. And for our framework, we try to construct the task to do the recommendation for each POI level. And for all the levels, we will do the multitask learning. And furthermore, for each task, it contains 2 subtasks. The first subtask is attribute-based representation learning, and the second subtask is interaction-based representation learning. And here I want to emphasize one more point is, in our second subtask, we try to capture the propagated information between POIs at 2 adjacent POI levels by using the attention network. So next, we are going to introduce the detail of our model. So first one is attribute-based representation learning, which aims to learn the feature representations for both users and POIs. And this information will be organized in the following loss function. So you can find actually in the left-hand, it aims to construct the information between users and their attributes. And similarly, we will try to construct the relation between POIs and their attributes. But the one important difference is that for POIs, because it will span in different POI levels, so that's why we try to sum this information together. And here L represents the total number of POI levels. And our second subtask is interaction-based representation learning, which aims to incorporate user POI interactions in our model. And we try to use an active sampling strategy. You can find actually for each visited POI, that is PG+, we will pair it with an inactive POI, PG-, which the user has never visited. And in this log function, we will try to maximize the difference between these two. And the matrix O represents the user and POI interactions. It will contain 2 parts, feature-based and historical information. Well, in the feature-based check-in matrix, it will contain this information, and you can find the details in our paper. Here I want to emphasize, we also model the inter-level POI feature representation propagated from child POIs from bottom to top by using the attention network. And furthermore, we also model the historical check-in matrix. And our intuition is users will visit those POIs which were visited before. And it will use a graph-based geospatial influence representation matrix to organize this information. And beforehand, we will construct a POI context graph where each node will represent a POI. And if there exists one edge between any two POIs, this edge will indicate the geospatial influence between these two POIs, such as the geospatial distance. And our logic is to model this is as follows. Suppose we have one POI to be recommended, and we can capture the geospatial information between the POI we aim to recommend and historical check visited POIs by involving the geospatial information. So here, let me introduce another important benefit of our model. Because sometimes users maybe recommended a lot of stuff, but they don't know why they are recommended this information. So in our model, we can provide three kinds of hints: user aspect hint, POI aspect, and interaction aspect. For example, in user aspect hint, suppose we recommend Chinatown to a user because we find the user has added dumplings as a favorite food in her profile. And in our experiment, we have used two city-level datasets. One is Beijing and another is Chengdu. You can also find the data statistics in this table. And in our experimental comparison, we also compared with 4 state-of-the-art methods. And we also use 2 common used metrics in our evaluation. One is precision and the other is NDCG. In the following experiments, we aim to answer 4 research questions. The first one is, how does our Ampere model perform compared with the state-of-the-art methods? And you can find in this table, we have listed the result under different performance metrics and different case and different data sets. The second question is, how does our Ampere model perform under different hyperparameter settings? And here we listed 2 different parameters and show the result here. So one is a matrix trade-off parameter and the other one is embedding size. And the third question is, how can our model derive the recommendation hints? So here we use the heat maps to show result. For example, in the first heat map, we can find the larger a value is, the darker the color its corresponding cell is, and the more important this feature will be. And the last research question is ablation study. And we try to remove different and some important components in our model and show the result as follows. So here are some references in this work. Thanks very much.